In Key Skill 4, we're going to be looking at some more complicated examples. So in this question, we're going to start with a bit easy and get harder. In this question, we've been asked to find both the area and the perimeter of the shaded region. Now, it's important to note that there is a right angle symbol here. If we start with the perimeter would be the arc length plus this length here. Now, to calculate this length here, because it's a right angle triangle, we can use Pythagoras Theorem. So we want to start with this length here. Now, both of these lengths would be 5, and this one would also be 5, because these are both, if you think about what the full circle would have looked like, these are both going to be radii. Radii is the plural of radius, in case you didn't know that. So h squared will be 50, and h will be square root of 50. So that will be that length here. Now, to get the arc length, we need to use the formula. So r in this case is 5, and theta, now remember, when you do theta, you need to have theta in radians if you're using this formula. So 90 degrees would be pi over 2. So the arc length would be pi over 2. So the perimeter would be this length plus this length. So it would be square root 50 plus 5 pi over 2. So if the question asks for exact area, you would leave it like that. Exact answers have square roots and pi's in them. Also logs and exponentials. Now, if that question asks for example, 2 decimal places or 3 significant figures, you just type it in. If it doesn't specify, I'd probably go with 2 decimal places. So that would be the perimeter of the shaded region. Let's have a look at what the area of the shaded region would be. We could start with calculating the area of the sector. And again, theta would be pi over 2. So it would be 25 pi over 4, and that would be this area. And what we're going to subtract from that is actually going to be the area of this triangle here. Now, because we've got a right angle here, we can use the formula for area of a right angle triangle is a half times base times height. This would be the height, and then 5 would also be the base, which would be 25 over 2. Now, if they ask for exact area, I would say 25 pi over 2 minus 25 over 2, or 25 over 2 pi minus 1. Or if you need a rounded answer, you could use this. Let's move on to something a bit trickier. I think this might actually be the trickiest question of this series. The last question is pretty hard, but I think this one might be a bit harder. You've been asked to find the area of the shaded region. So that's that bit. Just please note that it's not going to be enough to get the area of the triangle and subtract the semicircle, because you can see these little guys over here are not shaded. You specifically need the area of the shaded region, that little bit there. The first thing I'm going to do is calculate the lengths of these sides here. We've been told that there's a right angle here and there's an isosceles triangle. So we can do Pythagoras Theorem. We can say that 6 squared is equal to x squared plus x squared, if we call that length x. So 36 is equal to 2x squared, and 18 is equal to x squared. So x is the square root of 18, which is square root 9 times, I was going to say 3 there, whoops, square root 9 times 2, so that's 3 square root 2. The other way to do it would be to make it equivalent to your special triangle, which is normally 1, 1, square root 2. So in this case, so if this would be 6, you'd have to do 6 divided by square root 2 for the scale factor, and then you'd rationalize that as 6 square root 2 divided by 2, which would simplify down to be the scale factor must be 3 square root 2, and then you'd multiply that scale factor by this one. So either way would be completely fine. So now we know that the length of x would be 3 square root 2. The next thing we're going to need to know is what is the radius of this circle. You can see that this length here, 6, is bigger. So what I'm going to do is take the red, I like to put the radius in red, and know that where the triangle intersects with the circle, there's only one point of intersection. So this is a tangent to the circle. So if I pencil in the radius from the center to the point of intersection, I know that that must be a 90-degree angle there, because the tangent meets the circle. The tangent meets the radius at 90 degrees always. Now this is a rough sketch, guys. I'm not a great artist. That might be a newsflash for everyone out there. Now, this length has to be the same as this length because they are both radii, okay? And the missing angle here must be what? Well, let's think about it. That's 90, that's 90, that's 90. And inside a quadrilateral or four-sided shape, there's 360 degrees. So if you do 360 minus 3 lots of 90, that leaves you 90 left. So this must be a square. We've got 4 right angles, 1, 2, 3, 4, and we've got 2 sides the same. So we can calculate the area of this square if we can find the radius. In fact, if we get the radius now, this whole question is going to unlock, because we can calculate the area of the sector there and then subtract that from the area of the square. But we need to know the radius. So what we can do is we can say here, that must be radius, and here that must be radius as well, because we know it's a square, so all these 4 sides need to be the same. So what we're going to do now is work in these little right angle triangles here. And we can say that this length here must be square root 3 square root 2 take away r, because the whole thing was 3 square root 2 and that's r. So what's left here must be 3 square root 2 take away r. Now if we use Pythagoras theorem with this length and this length, we should be able to find this length here. So right now I'm just doing Pythagoras here to find this length here. That would be 9, 9 times 2 would be 18. So this would have been 3 times 3, 9, square root times square root 2, square root 2 times square root 2, so 9 times 2, 18. This would be 3 square root 2r, and this would be 3 square root 2r as well, so together you'd have 6. And this minus r times minus r would be plus r squared, and we've got another r squared there. So now we've got our expression for the Pythagoras theorem here. So if we just take this one, we can see that this problem is completely symmetric down the middle. So this length here, this green length here, must be 3. So we can say a squared plus b squared is equal to 3 squared. Now we know that what a squared plus b squared is, and then that needs to equal to 3 squared, which is 9. All we have to do is tidy up that expression. So we're going to have 2r squared minus 6 square root 2r plus 9 equals to 0. I'm going to put all of that in the quadratic formula with a equals to 2, b equals to minus 6 square root 2, and c equals to 9. So minus b will be plus 6 square root 2 plus or minus the square root of b squared minus 4 times a times c divided by 2a. I'm going to type that all in, guys. And that gives an answer for x equal to 3, or actually I should say that gives an answer for r equals to 3 root 2 divided by 2. I'm not going to bother to take the negative solution because I only want to keep it positive. Now this question becomes quite easy. All you have to do is calculate the area of the square, which would be r squared, which would be 3 square root 2 over 2 squared, which is 9 over 2. And then you have to subtract the area of the sector. Now we know that that angle there is 90 and we know what r is. So the area of the sector is going to be, so the area would be 0.5 times by 3 square root 2 over 2 squared, which would be 9 pi over 8. So that's the area of the whole sector. So that would be the area of this sector. All we have to do is do 9 over 2, which is the whole thing, and subtract the sector. A common denominator of 8, so times by 4. And we can factor out. And that's our final answer. That one was really tricky. And I've got another really tricky one for you coming up in question 3. In our last question, we've got to refresh our special triangles. Just to refresh, we had an equilateral triangle, a special triangle that was 2, 2, 2, and we ran a perpendicular down the line, down the middle here, which meant that this length here was 1. We did Pythagoras and got that this one was square root 3. Now we knew that because it was an equilateral triangle, all the angles were 60 or pi over 3. And when we cut pi over 3 in half, we're going to get pi over 6. So just to keep you refreshed about your special triangles, it's going to be important later. We've been asked to find the area of the shaded region. So we can see the area of the shaded region is going to be the area of the sector subtracted with the area of the circle. But to calculate the area of the circle, we need radius. So what it's important to notice is, again, that this is a tangent to the circle. So if we put the center of the circle being here, okay, we can join a radius at the point of intersection here, and that would be r. This length here would be 10 minus r. Also, guys, later on it's going to be important to remember that this must also be 10. So what we do is we join this up here and we pencil in our right angle like that. Now, if we look at this and we can imagine that this is 90, this is r, and this is now going to be pi over 6. So if we were to zoom in and draw that again, a bit bigger, what we've got is something that looks like this. Here we've got r. This angle here is going to be pi over 3. And this angle here, this angle here is going to be pi over 6. And this angle here is going to be pi over 3. So if we look at our special triangle, you can see these two are similar triangles because they have all the angles the same. So these must be a multiple of each other. So if we redraw them next to each other, we can see that the side that would correspond to 1 would be between 90 and pi over 3. So that would be this side that would correspond to 1. The side that would correspond to square root 3 would be between the right angle and pi over 6. And the last one, the hypotenuse, would be 2. So what you can do is you can work out that the scale factor must be r. So these sides must be, this must be 2r, and this must be r square root 3. Now, that's important because if you know that this is 2r, you also know that this is another r here, we can say that 3r must be the same as 10 because 3r is the same as the distance from the center of the circle to the circumference. So this and this also would both be 10. Now we've said that if that's r, by the similar property and the fact that this is a square, that this is a similar triangle, if that's r, that must be 2r. and that one there would in fact be square root 3r. So you can say that 3r is equal to 10, so r must be equal to 10 over 3. Now we can do the calculation for the area of the small circle. We can say the area of the small circle is equal to pi times r squared. So it's equal to pi times by 10 over 3 squared, which is 100 pi over 9. The area of this sector here is going to be equal to 1/2 times r squared times theta. Now, the radius of the sector would be 10 and theta would be pi over 3, which would be 100 pi over 6. So then we need to calculate the shaded area would be the area of the sector, the 100 pi over 6, subtracted with the area of the circle, 100 pi over 9. You just need to make the lowest common multiple of 18, so you would multiply the first one by 3 and the second one by 2. So your final answer would be 100 pi over 18, which you could cancel down by dividing by 2 to 50 pi over 9. And that's done. I hope you enjoyed that tricky question. Well done, guys. You stayed alive for those really tricky questions. I've got a whole selection of exam questions for you to have a go at, all the way back from 2001. So I'd really recommend you have a go at those before finishing this course out and starting the next course. I hope you enjoyed it. Please like, subscribe, make sure you've set up your profile on the website, all of that good stuff, and I'll see you in the next mini-series. If you have any requests for questions you want me to do, post it in the comment in the box below. Bye for now, guys.